So they have shown the recursion trace from 17 to 0, each one of which involves one multiplication except the last one, 0, right? So right now we are at a point where, okay, we get 17 multiplications, that is correct. So then what is the complexity? ON, all right. Now how would you justify it? C is 1. Okay, so which means that we have the following, right? So you have this, right? For n some and not, right? And you say that C is 1, okay? And then this one is 1. Okay, so at any point of time, you just need to show, okay, yes. That is correct. Now, do you have a proof for correct? So this is based on induction, is that right? Okay, all right. Okay, so the base case, what is your base case again? Power 0, all right. So, all right, this is equals to 1, okay. So in this case, we say x0 is equals to 1, all right, okay. So this one is correct, right? Because you expect 1, all right. Power 1, okay, is power 0 times x, is that right? Okay. You build, okay, how do you build up to n? Okay, yeah, so it's kind of correct. You just have to state it in a little bit of a different way because you want to state it in a general way, right? So which means that, okay, so what you're saying is that you're going to go from 0 to 1 to 2 and so on. So basically you establish a base case. So then you just want to go from one step to the next step. So let's express that step in a general way. So let's say if we believe that xn minus 1 is going to give us exactly this, right? Which means that it's correct at the point of n minus 1. So then you just want to show that it's also going to be correct at n. So now then we look at this, and it turns out that at n, what it's going to do is that it's going to produce the multiplication of x and the xn minus 1, right? And since if we believe that this is going to give us this, so then this is going to be xn minus 1. So this is a 1, right? So 1 plus n minus 1. So then this is going to be x to the power of n. So which means that if xn minus 1 give us x to the power of n minus 1, then calling it at the following step, which is n, is going to give us x to the n. And since you have the base case correct, so then by induction, this is correct. Okay, so it's not difficult, right? I mean, in this case, we're just stating something in a formal way. Intuitively, you kind of already know it. And I think that's kind of where we are getting at this, right? We just want to, first of all, getting you familiar with the notations and the language of induction, and that's basically proof for correctness for in-class exercise 1. Okay, at this point of time, any questions? Yeah. Yeah.
Let's say that if you divide, let's say, E x comma n,
yeah.
If you divide it n times by x,
1.
I think that's like that's good.
But how do you prove it? I mean, what you have is that you have a function, right? I give you an algorithm, and we want to know, does the algorithm produce the outcome that we want? And the outcome that we want is that this, if I'm using this algorithm, I'm going to get to the output, which is x to the n. So
also not like go the other way. Xn over x is xn minus 1.
Say that again. Xn over x.
So xn over x is xn minus 1 and all the way until 1. Is that possible?
Okay, so, but what is the claim there, and what is the step that you're trying to show? So if what you're trying to do is to find the root of something, then I would do something like that, right? So that means you're using by induction the root of something. Yeah.
So he has to follow like the sequence of like the power.
Because induction only takes one step. Actually, induction only takes one step. You go from n-1 to n, or n to n-1, depending on which direction you want to go. But you establish one base case, and then you take one step. So it's just like climbing a ladder. So you start at the bottom, as long as you can climb one step at a time, eventually you reach the top. That's kind of the concept. Yeah. Okay. Yes.
There's only one sort of multiplication. What would you do by induction if you say one step? What the next step is?
Say that again. Yeah. Say that again. Yeah.
It's like only one fraction there, right?
Yeah.
Multiplication.
Yeah.
So if the next step is, let's say, I don't know, there's like another case. What will you do there? Like even at all, for example.
Oh yeah, that's the next one, right?
Yeah.
Yeah, that's the next one. We'll get to the next group, right? And ask them to explain it to us.
So
Yeah. Okay. Yes. Okay. I hear ON and ON minus 1. Can you explain that again? Yep. So if n is 0, then there is 0. Correct, yeah. But your n is 0, right? So what we are doing here is that what we are doing here is not a proof of complexity. What we are doing here is just to show correctness. It means we are trying to show that if I execute the power function, I'm going to get to the outcome, which is x to the power of n. That's what we want to show. Oh, the number of operations, we're going to say ON. Yeah, because when it's 0, the n is 0, right? So n is 0 is 0, n is 1 is 1. So you just follow the n. Yeah. But in any case, even if you get to ON minus 1, then the minus 1 is a constant. You just drop it. Then you come back to ON. Yeah. Okay, all right. Okay, we don't have a group 7, but we have a group 8, right? So let's talk about the group 8 for your solutions for the in-class exercise 2.
Okay, so for the recursion case, we
Yep.
got 7 multiplications.
7 multiplications. Okay, how do you get 7 multiplications? So
started from 317.
All right.
We went down 1 to 3.
Okay.
Then we went down 1 to 3. And then every case that has an odd number on top, we have a additional times.
So we have this one and this one, right? But the second one only if odd, right? Yeah.
So for the 17 case and the 1 case, we have two multiplications.
So you have 2 here and you have 2 here.
And then the rest will be 1.
1 here, 1 here, 1 here. How about this one? 0?
0 is because 317 actually doesn't have multiplication in a sense.
Right, but does it go to 0?
So 0 is
So it will go to 0, doesn't would it? So you go 17, 8, 8, 8 to 4, 4 to 2, 2 to 1, but 1 divided by 2, right? You still have one case there. It will go to 0, right? But in the case of 0, you still have a function call, but there is no multiplications, right? So then you get a 0, yeah. So in that case, the total number is? Okay, so that means 7, right? Yeah, okay, 7 multiplication, yeah, that's correct. And that's less than before, right? Before you have 17, now you just have 7. So what is the complexity? Log n. Okay, all right, so explain it. Like, how do you get log n? So you can divide n, okay, by 2, n over 2, right? N over 4 all the way until you get to 1, and then you go to 0, right? Okay.
So times you divide it will be log 2n, and then
Okay, so log 2n.
Yeah. For this, we assume the worst case scenario, so which is like 2 comparisons at each stage.
Okay.
So it's 2 log 2n.
So why is that the worst case?
First, the most number of multiplications at each step can only get size 2.
Okay. Okay, so you're saying there are log 2n steps, and each time you're gonna have up to 2 multiplications. All right.
Yeah. But for the proving part, we didn't get that.
Okay. So let's settle this first. Okay, log 2n. That is the maximum number of multiplications you could have, right? So which means that you have a function. Oh. So you have a function fn, right? Which is the number of multiplications that you're going to do, right? So then this is going to be bounded by 2 of log 2n, right? So of course, when n is equals to 1, this is not true, right? Yeah, but for some n naught, this is going to be true. And so you have the c. So you just want to show that it's going to be bigger for some n naught. So then in that case, you can probably pick n naught somewhere maybe at 2, or yeah, at 2, let's say. So log 2 of n is 1, so that's going to be 2. So it's still not correct, right? So then you can go to 4, for example. Yeah, and so on. But anyway, yes, correct, right? So you can show that through some c and some n naught, this is going to be O log n. So we don't need to write the 2, right? So we just say log n. Yeah. Okay, all right, that's correct. Okay, so okay, let me clear it up a little bit, right? Then we can talk about the last part of it. All right, so in this case, we want to talk about the proof of correctness for this case. So now when we say proof of correctness, so what we want to do is the same as before. We just want to show that we have px to the n, and this is going to produce x to the power of n, right? So, and if it does, then we call it correct. So we can use the same proof method as before. We can call it induction, right? But induction in the previous case is to go from n to n minus 1, or n minus 1 to n. So, and each time we just need to increment it by another x. Now, if we look at these cases, we realize that the decomposition, it doesn't go from n to n minus 1. It goes from n to n over 2. And it turns out that we are going to do something a little bit different if it is odd or even. So in these cases, we can split them into the 2 cases, and we're going to start with the simpler case. And the simpler case is the even case, right? Now, let's say, what does it mean to be even? So let's define this, right? So let's say the even n, right? In the even n, which means that n itself is going to be 2k for some integer k, right? That's the definition. So we say n equal to 2k for some integer k. Now, let's say we're going to do this by induction. So the base case is the same, right? So we just have to show that for n equals to 0, so it's going to return xn, which is equals to 1, which is by definition, because you kind of have the base case here, that is going to return 1, right? Now, the following case is going to be, okay, so let's write this down. This is okay, so let me see, all right. So this is what we consider to be the base case. So then we want to do the inductive step. Now, the inductive step, here we base on the decomposition that we have there. So we are going to say that let's accept this for n over 2, right? For x n over 2, and let's say this is going to give us the exact outcome that we want, which is x to the power of n over 2. And because n is 2k for some k, so then we know that this is equal to x to the k, right, for that integer k. Okay, so then we are trying to show what is the next step. The next step is that, well, we're going to show it for x to the n. Now, if we look at what the algorithm is actually doing for x to the n, I'm going to store it in some partial variable. So I'm going to multiply it to itself. So I'm going to multiply it to itself. Okay, so in that case, I'm going to basically take whatever outcome I get from here, right, which is x to the k. So I'm going to multiply it to itself, which means that I'm going to have this, right? So this is based on the outcome of the algorithm. So since xk, so that is going to give me x2k, right? So we started out with n being an even number, and that is 2k. So there's going to be x to the n. So more or less that's just that, right? So we can argue then, based on induction from n over 2 to n, then we can get the correct answer, given that the n over 2 is also producing the correct answer. Now, this is the case of even n, right? Now, you can kind of get a sense on how to do this for the odd case, right? Okay, so let me see here. So case number 2, we have the odd n. So this particular case means that n is equal to 2k plus 1, right? So that's the definition of the odd number. So you got 2k plus 1 for some integer k. So now the base case, exactly the same. So n equals to 0, we get x to the power of 0 equals to 1. Okay, so correct, right? Now the inductive case then. All right, okay, so we are going to assume that this is correct, right, for n over 2. Okay, now, so let's say if I get it at n over 2, so this is going to give me x n over 2, but the n over 2 here is an integer, right? So which means that this is going to be x 2k plus 1 over 2. So because this is an integer division, so the remainder, I'm not going to keep that, right? So I'm going to get x to the power of k. So if n is an odd value, odd integer, I'm going to get x to the power of k, you know, if it's n is equal to 2k plus 1. So then I'm going to produce it for n then. Now, since this n is odd, there's going to be an extra multiplication, right? So this is coming from this particular condition in the n mod 2 equals to 1, which means odd. I'm going to add another x there. Not add, but I'm going to multiply it again. So then in this case, I'm going to multiply xk with itself plus another multiplication of x. So then I have k and 1, right? So that is x to the power of 2k plus 1. That is x to the power of n. So then that case is still correct, right? So that's what we mean by proof for correctness. Now, it's not actually a very complicated thing, right? So sometimes it's just a method of putting this into the correct inductive formalism, and then you get more or less the argument that allows you to do that. Now, as far as we're concerned, the function here, we are saying this, we may not exactly know what's going to happen from that function. Of course, we look at it, we see it, okay, we say, okay, that looks correct. And indeed, we are using simple function like this exactly because you can analyze it for correctness even by looking at it. But the point is that you may end up sometimes with more complicated stuff, or with particular cases where even some of the cases are black boxes that you don't have access to. So in that case, then you got to make some kind of inferences based on what you can do. And let's say in this case, you can do proof by cases. Okay. All right. Any other questions? Okay. Let me see in the Teams. Okay. So in inductive step, why is x n over 2 is equals to x to the power of k? Well, because n is equals to 2k plus 1, right? And so n over 2 is 2k plus 1 divided by 2. So that is why we have k. Okay, can you please explain pxn step? Okay. Okay, so the inductive step, works in the following case, right? We are going to show that I can go from a smaller case to a bigger case. And I'm going to assume that if the smaller case is true, then the bigger case is also true. So now the smaller case here is going to be n over 2. So if n is odd, so it's 2k plus 1. So 2k plus 1 divided by 2. So since plus 1, right? So we know that the first part, 2k, is divisible by 2. And the division will just give you k. The second part, 1, is not divisible by 2. So in terms of integer division, it's going to go to 0. So that means that you're going to get x to the power of k. Now, that is the base, that's the smaller case. Now, the bigger case is that px to the power of n, right? So let's say we execute this. Then we look at what the algorithm is actually doing. It's actually taking n over 2, right? So which I'm going to evaluate that. So, but if we evaluate that part of it, then I'm going to get the output that I get from the previous function. And that just now we say is going to be x to the k. But we multiply it to itself, right? Because the algorithm is going to have this part that is a partial times partial. And the partial was the n over 2. So it's going to be multiplied by itself. So which means that if one of them is x to the k, then another one of them is going to be the same, which is also x to the k. Then because it's odd, I have to add another x here. Well, multiply another x. So then I have k and 1. So that is going to sum up to 2k plus 1. And 2k plus 1 is equal to n, because that's the definition that we begin with. Okay, so, okay, why is it not xk plus half? Okay, because this is integer division. So this is an integer division. This number is an integer, right? So in the integer, you're only dealing with integers. You don't deal with the float or the double or anything. So which means that when you give it something like 5 divided by 2, it's not going to give you 2.5. It's going to return another integer, which is just 2. So the half is going to disappear because it's integer-based division. Now, if you use this algorithm and you write it as float or double, then of course it's going to be different. Then in that case, then we get a different outcome. Yes? Say that again.
Why do you only consider the result equals partial when you add it to a bigger case?
When I expand it to a bigger case. So basically what we are saying here is that if I accept this to give me the correct answer, then I must accept that this is going to give me the correct answer. So that is the inductive step. So we take a look at one piece of the component, and we say that if I can solve that problem, and if I solve that problem correctly, then the bigger solution that makes use of that particular component is also going to be correct. So that is the inductive step. We go from n over 2 to n. So I have to assume that this is correct for me to conclude that the bigger method is correct.
That's why the second part, you have to consider the rest of the else statement.
Yes.